And today we have to study the frequency response of BJT amplifier, right? So I guess you can see the circuit in front of your screens, right? So let's build this circuit first, and then we will simulate it one by one, okay? So this is my LTspice window. So if you're starting for the first time, what you have to do is you have to go to new schematic, click on the new schematic part, okay? So I've already done that. And now you have to go to the components. Here is my component over here. And from there, I have to type BJT, okay? Or I have to type NPN, sorry, NPN. So once I type NPN, it's a bipolar NPN transistor. I'll press OK and I'll drag it onto the schematic, okay? If another one comes, press escape. Clear? You can zoom out a little so that other components can also fit in. Now next is we will require registers, 4 registers. It's a voltage divider bias, right? So I'll be requiring 4 registers. So what I will do is I'll take the register directly from here. Okay. So I'll place one register over here, one over here. This is R2 and this is for RE. Okay. So I have placed 4 registers in the circuit. Now I have to connect them together quickly. So I'll go to this wire. Okay. I'll go to this wire and I'll connect them together. So here it is. I made the connections. And don't forget to add the base connection also, right? Base has to be connected to R1 and R2. And now we have to name them together, name them, right? According to the circuit, this is R1, R2, RC, and RE, right? So we will do that quickly. This is R1. This value is given as 40K. In your write-ups, it might be different, so use that value. This is R2, and this is 10 kilo ohm. Okay, now RC value is 4 kilo ohm. So this name of the register is RC, and its value is, if you have to select the value, right click on R and then select the value 4K. Okay, RE value is 2K, right? So I'll right click over here, I'll go over here and I'll type there RE, and the value of RE is 2 kilo ohms. Fine. Now we will complete the remaining part of the circuit. So I have coupling capacitors, input coupling capacitor CC1, output coupling capacitor CC2, and bypass capacitor CE. I have to connect it. So capacitors, I can take it from here and I can drag it over here, right? This is my CE. Now I'll require to rotate the capacitor. So how to rotate it? On your keyboard, press Ctrl R. Ctrl R will rotate the capacitor. So one capacitor over here, another capacitor over here. Okay, fine. Now next is we have to connect the AC input source. Okay, AC input source, and one more register is required at the output, RL, right? So first select a register. Register RL will be going over here, somewhere around here, right? This I will rename it in shortly. So next is we have to apply the AC source and the DC power supply, right? So what I will do is I'll again go to the components. From here I'll type voltage. Okay, I'll click on OK. I'll drag a voltage over here. Another voltage I'll require for power supply. So I will keep it another voltage over here. Okay. Now what we will do is we will connect them. We will quickly connect them. So those who are doing along, please do it together. Fine. And this is also connected. Now let me connect the bypass capacitor. I mean, I can connect a separate ground also, that will do. Then I will be connecting the input coupling capacitor, and a separate ground will do. Don't forget to add the ground. So ground will come over here, it will come over here, and it will come over here. So join them with the wire. Okay, very quickly we have done that. All the connections are completed except the DC power supply. So DC power supply connection, I will be connecting it in this manner, and I'll be having a dedicated ground over here. All the grounds are together only, right? So I'll be renaming now. VCC is 20 volts for me. For your case, it might be different. So be vigilant about it. I'll right click and mark over here 20 volts. Okay. This is my coupling capacitor CC1. So I'll mark CC1 over here, and the value is given as 10 microfarad. Okay, so I'll give the value as 10 microfarad. Now next is CC2. This is CC2. The value of CC2 is around 1 microfarad. So I'll right click over here, I'll write 1 UF. 1 UF stands for 1 microfarad. This is bypass capacitor CE. So bypass capacitor CE has a value of 20 microfarad. So I'll type over here 20 UF. Okay, and this is my load resistor RL. So this is RL, and its value is how much? Its value is, I guess, how much it is. Let us check it at. You have to check it at your own values in your circuit. So this is 2.2 for me over here. So this will be 2.2K. Okay. So all the circuit connections are done. Now we have to select the AC supply source. That we will do it later. But first of all, you have to select the BJT. So BJT has to be selected, and that is BC547B. Now how to do that? Right click over here. Go to pick new transistor, and from here scroll down until you find BC547B. So as you can see, this is BC547B. So this you have to select and click on OK. So your BC547B is selected now. Okay, and this completes the entire circuit. Fine. So what we have to do now is, in our experiment there are two parts, right? So first part is, let me maximize the screen now. So first part is, we have to determine the common emitter amplifier with bypass capacitor. That means that if your capacitor CE is connected and you do your analysis, transient analysis and frequency response. There are two analyses in a circuit, right? Transient analysis and frequency response. So for bypass capacitor present, you have to do that analysis, and that is part one. Part two will be common emitter amplifier with capacitor CE unbypassed. That means, without bypass capacitor CE. So that means you have to disconnect this bypass capacitor and complete your entire experiment again. Okay. So let us begin with a frequency response. Now, for the frequency response, what you have to do is, first of all, for plotting the frequency response, what you have to do is, first of all, right click over here on the AC on this V1 source. Let me call it as VS itself. Let us see what we have called it in the circuit, VS, right? So let me call it as VS. Okay, fine. Now I will be right clicking over here, go to advanced, and here you see small signal AC analysis. AC amplitude you give 1. You give 1 and click on OK. That's it. So this AC space 1 will come. That means you all have given the amplitude to this input as 1. And since, what is frequency response? Frequency response means you have to study the response of the amplifier for various frequencies, and you want to check the gain of the amplifier. So the gain versus, I will just show it to you, 1. So frequency response means I will just plot a frequency response for you all. Okay. So this is how the frequency response will look like. So your x-axis will be frequency, which will be normally a log scale. Okay. And your y-axis will be usually the gain. Okay. AV is the gain, which will be in dB. Gain will be in dB. Okay. So these were the various frequencies. You will have frequencies of 10 Hertz to around 100 megahertz. Okay. And you're testing the response of the amplifier in such a way that you are testing whether the gain of the amplifier, where it is dropping and where it is remaining constant for various frequencies. Okay. So this is what do you mean by frequency response. Fine with it? So this is your frequency response over here. Frequency response. Okay. Yeah. So now let's continue. So what we have to do is, I will show the steps in the over here, right? I'll be showing you all the steps how to do it over here. But first understand what you have to do in the simulation part. So for the simulation part, for the frequency response, you cannot give any frequency. You have to do it this way. Again, I repeat, right click over here and select the AC amplitude over here as 1. Okay, why it is selected as 1, that also I will let you know. Okay, now you have to click on simulate, click on run. So when you click on run, there are various simulations, different simulations are there. One is transient simulation, one is AC analysis. So transient means whenever you want to plot V in versus time and V out versus time. Okay, but we don't have to do that. We have to do the frequency response. So for frequency response, we have to select over here. Okay, we have to click on the AC analysis part, and we have to select the type of sweep as decade. Okay, to select the type of sweep as decade, select the number of points as let's say 100. Start frequency will be 10. Stop frequency will be 100 mega. So how do you write 100 mega? If you think you write capital M, you're wrong. You have to write capital MEG. So LTspice will take the reserve word as MEG. If you write capital M, it will take it as small m, which is milli. So you don't have to do that. So write 100 MEG. Okay. I repeat this step again. You go to simulate, you click on run, you go to AC analysis, select the type of sweep as decade. Number of points per decade you can select as 100. Start frequency will be 10. So what is the meaning of start frequency 10? I'll explain it to you. Stop frequency will be 100 megahertz. Okay, and after you have done that, just click on OK. So when you click on OK, a blank screen will appear. It's a Semilock plot. Okay, with a frequency starting from 10 hertz going till 100 megahertz, right? And it's a Semilock plot. I will explain what do you mean by Semilock plot. So what happens is you cannot plot so many frequencies together of the same magnitude, right? It will be easier to plot 100 hertz and 10 hertz together on a simple normal graph paper. But if I have to plot 10 hertz, 100 hertz, 10 kilohertz, 1 megahertz, 100 megahertz together, then I have to use a log scale. So basically it means that x-axis is a log scale over here, right? Now listen carefully what you have to do next. Now you have to just name this transistor carefully. So I have to label this node over here, label this node. I'll close this plot again. Now I have to label this node. I have to tell that this is V in and this is V out. How will I do that? I'll right click on the wire. I'll click on the label net and I'll call it as V in underscore my name. So you will write your name over here. V in underscore your name, and I'll select the port type as input. And then I'll click on OK. So this I will place it over here. Okay. This I will place it over here. Again, I repeat, I'll right click on the wire. I'll click on the label net. You label that, you name it as V in underscore your name, and you select the port as input port. Okay. Fine with it. Again, similarly, this is input and I will be doing it for output. So here what you can do is right click on the wire, click on the label net. Here I'll write V out underscore the name. Okay. And what is the port type? Output port. I'll select OK and I'll attach this over here. So this labeling part is important. It's very, very important. I will tell you the significance of it. So much, this much is completed, I hope. Okay. Everyone has completed this up till here. Any doubt? Please acknowledge if you have completed up till here.
Yes, sir, completed.
Okay, good. So now let's continue with the frequency response. So I'll run it over here, right? I'm getting the readings from 10 hertz to 100 megahertz, right? Now what I have to do is I have to right click on the blank screen, go to add trace, and here you see the output will be there, which you have defined the label, right? So select V out, V out value with your name, okay, and click on OK. Right? So as soon as you have clicked on OK, you will get these readings. You will get this graph. Okay. So your this plot over here is my magnitude response, and the dotted line is my phase response, right? So what I will do is I'll right click over here and delete the phase plot because I only want the magnitude plot. So over here, what I shall do is it's basically starting from let us start from 100 hertz. Okay. So let me start from 100 hertz. Start frequency, let me start from 100 hertz and I'll simulate again. So you're getting in comparison now, proper, little proper. But here the readings, I mean, you can see that the graph will go more, right? So what I will do is I'll change this x-axis 500 hertz. Instead of 500, I'll take it as 100 megahertz. I'll take it as 500 megahertz. Okay, and I'll simulate it again. Yeah. So now you are getting a perfect plot. I can even start from 10 hertz. So again, I'll go back and I can start from 10 hertz itself. Okay. Yeah, if you start from 10 hertz, yeah, you can take this. There is a problem over here. So let me start at 100 hertz itself. No problem at all. So that I can see a perfect inverted tub like graph. Yeah, here it is. This is proper, right? So what has happened over here? I have defined my range of frequencies in the x-axis from 100 hertz to 500 megahertz, right? And what is in the y-axis? Y-axis is my gain in dB. Okay. So as you can see over here, we had a similar kind of a plot over here, right? Let me show it to you. Yeah. So see, we got the same plot over here also, right? The y-axis was gain in dB. So as you can see here, it is gain in dB, and this is x-axis is my frequency, which is in the log scale, right? So yeah, that is just this is a semi-log plot. Why it is called as a semi-log plot? X-axis is in the log scale, and y-axis is linear scale. Okay, but y-axis is a dB. So you will say how this is a gain. Okay, why you will say why this is a gain? This is a gain because what is the gain of a system? What is the gain of a system given by? Let me write it over here. Let me use a blue color over here. So a gain will be given by AV, and that will be equal to your voltage gain AV will be equal to V out upon V in. Okay, output voltage upon input voltage. You remember over here in this amplifier, output is a AC and input is also a AC. Okay, in this case we have written Vs, so that is fine. We can overwrite over here Vs, input as Vs. So V out upon Vs is my gain of the system. Now you will say why it is coming in dB directly in the plot over here like this. It's coming in dB, right? Why it is coming in dB? Because while simulation we have selected that over here in the decade form. Okay, and if you go over here in the plot, if you right click over here, you have already selected in decibel form. Okay, and if you select a logarithmic, it will be in logarithmic, so it's already in decibels. And why why don't we have to write over here V out upon V in? Okay, why don't we have to write over here V out upon V in? So basically here it should be V out upon V in, na, or Vs. So why it is not over here? Because in our analysis we have took over here, as you can see, input Vs as 1. Okay, so if input Vs is 1, then what is happening over here? This value over here, we have took the magnitude as 1. So gain is nothing but output itself. That is why. Okay, that is why here when we plot this graph, we don't have to write only V out only, and V out will be equal to the gain, right? Because Vs is 1, we have selected 1 only now over here, right? Amplitude is 1, so V out upon 1 will be V out only. So this V out is nothing but my gain of the system. This much very, very clear, everyone? Okay. Now we'll come to the frequency response. So in your in your write-ups, this will be the table given to you, right? So under the part 1, that is CE amplifier with bypass capacitor CE, you have to complete the frequency response. Okay, and what does the frequency response is about? Input signal frequency, then there will be output voltage V out and gain in dB. So first of all, we will concentrate on the input signal frequency and gain in dB. Okay, so what you have to do is you have to take the range of the input signal frequency in this fashion. You have to take it as 10 hertz first, then 30, 50, 70, 100 hertz. Then you have to follow the same pattern: 300 hertz, 500, 7, 1 kilohertz. Okay, 1357. Okay, then again 1 kilohertz, 3, 5 kilohertz, 7 kilohertz, 10 kilohertz. Then 30, 50, 70, 100 kilohertz. Then 300, 500, 700 kilohertz. then 1 mega, 3, 5, 7, 10 megahertz, then 30 megahertz, 50 megahertz, 70 megahertz, and 100 megahertz. Actually, we have taken the reading till 500, so we have to take it till a few more readings over here. You have to take it till this will be 300 megahertz, okay, and finally 500 megahertz. Two more readings have to be added over here, and that will complete the list. Okay, so you have to go by the sequence 1, 3, 5, 7. Okay, 1, 3, 5, 7 is in the power of 10, in the power of 10, and you will have this many plenty of readings. So this is the frequency response plot. What are we trying to do is we are trying to change the input signal frequency from very low frequencies. Now this is called as very low frequencies. Let me mark over here. Okay, sorry for that. So this is low frequency. This is termed as low frequencies. Okay, right, you can extend it over here also, and ahead we have very high frequencies. Anything greater than 10 megahertz is a high frequency, so this is a high frequency range. So these are higher frequencies, and in between that you have mid frequency, I mean intermediate frequencies, right, in between low and high. So in the graph over here we have low frequencies over here we have high frequencies, and this is mid frequency region. Okay, I will elaborate in detail. So in the plot also, this is the low frequency region over here, this is the mid frequency region, and this is the high frequency region. Okay, so now let's start taking the reading. How to take the reading now? Let me explain. Okay, so what you need to do is, let me just I hope this is visible, right? Both the screens are visible. Okay, let me start taking the reading. So let's take the input signal frequency as 10 hertz. So how to take the reading? You have to measure the gain value, right? So what you have to do is you have to right click on this cursor and drag it. I mean, right now it will show you the frequency and magnitude also. Ignore the phase, ignore the everything else, only concentrate on the frequency and the magnitude. So you bring your cursor to 10 hertz, 10 around 100 hertz. Let's say 100 hertz. So we have not taken till we are starting from 100 hertz. So that's fine. You can also start. I have taken initially from 100. I have started from this thing 10 hertz, but that's fine. You can take it as 100 also. So let me do the required changes. So let me also start from 100. So these readings I will cut and I'll start from this only. So this becomes my low frequencies now. And let me just, take the table a little down so that it is clear to you. Just a second. Let me start, take this part a little down. Okay, now it is proper. So let's continue. We were starting with 100 hertz. So I will also do the same over here. Right. At 100 hertz, we have to note down what's the value of the gain over here. So here at 100 hertz, earlier I was getting at around 24.34. Okay. I mean, here I was getting with the values. I mean, you can note it down over here. So I will remove these readings over here from that. And then you can also add it your own readings. Okay. Let me do that quickly. Here there were earlier readings, but with RSIC present, but the RSIC is not present now in your circuit. Okay, I will show you any two sample readings. Okay, remaining you have to complete on your own. Okay, is the graph and the screen both visible together? Can someone confirm?
Yes, sir.
Yes.
Okay, now please concentrate over here. It will be about your readings now. Okay, at 100 hertz, what's the value I'm getting of the gain? 24 point something, right? So here it is 24.38. So what I will do, I'll go in the table, very simple, and against 100 hertz, I will write 24 point, how much? 38 dB. Okay. Now let's go to 10 kilohertz. I will take one more reading. So this way you have to go to 300 hertz, nearby 300 hertz, and measure the reading. Okay. So let me show another example at 700, nearby 700, right? So nearby value will also do 701. So 700 hertz you are getting 36.79. So you should write over here at 700 hertz, its value is, gain is 36.79 dB. So this way you can fill up the table. Okay, this way you can fill up the table. Now let me take one more value, one more sample value. Let me take that. Okay, so let me go over here. Let me take it as around 100 kilohertz. Around 100 kilohertz, what's the value? So what I will do is I'll go over here, drag the pointer, and I'll go to 100 kilohertz. I'll adjust it until it is 100 kilohertz. Nearby 100 kilohertz will also do. So I am getting 102, that's fine. And I'm getting the gain as 38.46. So at 100 kilohertz, my reading is how much? 38.46 dB. Okay, so everyone understood how to take the reading of gain in dB, right? Any doubt in this? Please positively confirm from your side whether you have understood this.
Understood, sir.
Okay, good. Now I will tell you how to take the reading of the output voltage, right? Now basically what we have done is, listen carefully now. We have taken the circuit over here. I mean, let me do this. Yeah, we have taken the amplitude as one. Okay, for a convenience, so that you know directly we can write down the gain, because gain is V out only now. But actually, in reality, we cannot apply. This is just for the testing purpose, which we have applied the gain. I mean, AC amplitude as one. But in reality, it's a small signal amplifier. If we apply a gain of 1, the gain of a BJT amplifier is more than 100, more than 50 or more than 200 also. So we cannot have a gain of 1. In reality, we have a gain, very less gain. So for measuring the output value, realizable output value, what you do is you right click over here and go to AC amplitude and write over here 40 millivolt. Okay, you write over here 40 millivolt, 40 M. Okay, and now if you simulate again, you'll get the same plot. You will say, what is the difference? The difference is that now I want to measure the value of V out, right? So what I will do is, change I have done. So I have right click on the AC input Vs. Instead of 1, I have given 40 millivolt. This is to measure V out alone, with the input being how much? 40 millivolt. Okay, so AC input is 40 millivolt now. And now if I plot again the graph, what I'm supposed to get? I'm supposed to get a frequency response plot, right? Here, what I will do is I'll right click on the y-axis, and instead of decibels, I'll press logarithmic. Instead of decimals, I'll press logarithmic, and let's press on OK. Press on OK. Fine. So as you can see, you get a logarithmic plot. Now you take the reading for the output value, V out. Is this step understood? Everyone has completed up till here? Please confirm. Or shall I repeat anything?
Sir, the last part.
Okay, fine. So what I want to do is I want to measure output voltage V out value, right? So earlier it was for gain we have taken AC amplitude as 1, but right now we are measuring the output with respect to the input amplitude. So the AC amplitude over here we will give it as 40 millivolt. So you go over here and select it as 40 small m and click on OK, right? And then what you do is I'll run it. I'll run it again. So you'll get a blank screen again. You right click, click on add trace, and you click on the output, V out, and click on OK. Remember, we are not measuring the gain. If I keep it V out only, I have to divide it by V in, that will be gain. That will be the voltage gain. But I don't want the voltage gain. What I want is, I only want the output amplitude. Are you following what I'm saying? Now right click over here on the y-axis over here. Right click on the y-axis, and instead of decibel, select logarithmic. Select logarithmic and then click OK. Is this point clear to you now? Yes? Can someone confirm?
Yeah, sir.
Okay. Now we have to measure this readings. Okay. So maybe in the last practical turn, I have showed you some different technique, but this is more efficient form. Okay. So you follow this technique now. And how will you have to continue further? You have to continue further by taking the cursor over here, right? Now this will only show you the output voltage value in magnitude form, okay, with response to the input. So I have to again go to 100 hertz and I have to measure this V out value. This is the magnitude, V out value magnitude, okay, and I have to write it over here. So let me take the pen and write down the values over here. So at 100 hertz, what's the value? 663.67 milli. Okay, so its value is 663.67 millivolt. Okay, and it's only showing the magnitude, huh? So it's basically showing the magnitude this way. Okay, in reality the output will be out of phase, so remember. And while doing this, what have we assumed over here? We have assumed that our V in value over here was 40 millivolt, right? It was 40 millivolt and we have taken these readings. Now let's check the value at 700 hertz. So I'll move this cursor further and I'll select 700 hertz, nearby value. Yeah, 710 will also do, no problem with that, right? Don't struggle with exact values, nearby value will do. Its value is how much? 2.77 volt. No unit is there, so it's volts actually directly. So here I will write it as, at 700 hertz its value is 2.77 volt. Okay, so that's the value which I'm getting over here, 2.77 volt. Now I will take one more reading. I'll take the reading at 100 kilohertz. Similarly, you have to take the reading at all the frequencies, okay? Then I'll take it as 100 kilohertz. So let me go to 100 kilohertz. So till it reaches 100 kilohertz. So this is around, yeah, 102 will be fine. No, don't struggle with the exact value of 100. Its value is 3.35. Okay, at 100 kilohertz, its value is 3.35. So let me write it over here. 3.3539 volt. Okay, so in this way you will complete this table. Remember, this output is in magnitude form, right? So we have to consider only the magnitude of it. Sign won't be present, so that's why I've written over here magnitude sign. So have you understood how to complete this table and how to take the reading in this with the for this plot? Can someone confirm please whether you have understood this technique? Yeah, hello. Can someone confirm whether you have understood this technique and successfully you can take these readings as it is?
Yes, sir.
Okay, fine, good. So frequency response part will be completed mostly, but there is one more thing which you have to do. Now let me go back to over here and let me tell you what is the next thing we have to do. So as your part of the experiment, what you need to do is you need to also check the FL value, the lower cutoff frequency. Then you have to check, you have to measure FH value, and then you have to measure the bandwidth. Okay, you have to check the bandwidth. Now let me explain it to you. How will you get that? So let's say that you have this frequency plot. I hope that the screen is quite visible to you. Let me keep it a little slightly near. Yeah. So now let me draw the frequency response plot in rough manner. Okay, in manner of speaking. So this will be the gain in dB. This is gain in dB, and this is F in log scale, and this is a semi-log scale, right? And you are getting the plot which looks something like this. I mean, let me draw it again. Correct? Similar to that, now you are getting the plot. See over here.
Right,
Exactly
sir.
in the same fashion you are getting. Now I will explain it to you how you measure this. Now listen very carefully. I have to, I mean, this is the maximum amplitude. So this maximum amplitude will be some value. Let's say that that value is around, for example, for my case, what I'm getting maximum amplitude. Let me check. Earlier, what I was getting around. Let me go back over here. Okay. So for measuring the bandwidth, we have to go back to 1. So go back to amplitude as 1, AC amplitude as 1, and again you plot the graph. For measuring the amplitude, I mean the lower cutoff frequency FL, higher cutoff frequency FH, and the bandwidth. You have to go back over here, frequency response plot for V out value. Click on OK and delete the phase plot. Okay, so let me check what's the maximum amplitude I'm getting, and it's remaining constant that value. I'm getting around 38.47, let's say, right? So let's say that this value over here, let me write it over here as how much it is. 38 value is how much? This value 38.47 maximum value, right? So this is my maximum value of gain. Fine. So what I have to do is how to measure the bandwidth now. Listen carefully, and how to measure the lower cutoff frequency. What you need to do is you need to come 3 dB down. So let's consider hypothetically that this is 3 dB down. Okay. Let me draw it hypothetical line over here. So let's say this is 3 dB down. Okay. Let me just expand it a little more so that you will understand greatly. Yeah. So this is 3 dB down. This I'll mark it as 3 dB. Okay. This is marked as 3 dB down. So what is 3 dB down then 38.47? What is this value over here? This value will be, this value over here will be 35.47 dB. Okay, so in your case, this value might be different, but you have to go 3 dB down, and whatever frequency you are getting over here, okay, you might be getting over here some frequency in the x-axis, right? So I have to go down. This frequency over here, this is my FL value. Okay, this frequency over here, this is my FL value, and this frequency over here, this is my FH value. Okay, this is my higher cutoff frequency, FH. So let me add the values, add the names over here, right? This FL is my lower cutoff frequency, is my lower cutoff frequency. Okay, and FH is my higher cutoff frequency. Okay, and how do you define bandwidth? Bandwidth is BW, which will be higher cutoff frequency minus the lower cutoff frequency. Okay, is this clear how to measure the bandwidth from the graph? Any clarification more required over here? You have to go 3 dB down, and then you have to locate at the lower frequency and higher frequency, mark the points FH and FL, okay, and measure the bandwidth. Now I will be showing you how to do it in the plot which you have obtained, right? So basically you have a maximum value of 38.47. So you have to go 3 dB down. Let me maximize the screen and show it to you. So you have to go 3 dB down, that is 35.47. So I'll take it in the lower range, 35.47, remember, 35.48. Yeah, 35.48 will also do. It is quite close. Okay, at 35.48, what's my value of frequency? 483.95 hertz, right? So this is my FL. This is the value of FL. Okay, so let me go over here and write it down over here. That is the value of FL. So what's the FL value I am getting over here? FL value I am getting over here is 483.958 hertz. Okay, is lower cutoff frequency clear to you? How to measure that? Yeah, clear? Someone please confirm finding problems in determining the lower cutoff frequency, right? Now it is clear to you. You have
Yes,
to
sir.
go 3 dB down. Similarly, I'll go up and go to the higher frequencies. Here the highest value of gain is 38.47. So again, I have to go 3 dB down. That will be 35.47. So I'll go over here slowly, and I'll get 35.47. Yeah, nearby value will do. Okay, 35.56 I'm getting. 35 point, yeah, 35.47 I'm getting 35.44. That will do. So this frequency over here, which is around 77.02 megahertz, this is my FH. Okay, this is the value of FH at 3 dB down at a higher frequency range. So I'll write the value over here. It is, how much it is? 77.02 megahertz. How much is megahertz? 77.02 into 10 raised to 6. Okay, understood how to measure it? And when you do so, take the print screen. And when you take the print screen, take the full print screen, including the date and time. Don't crop anything. So whenever you take the print screen of your own write-up, okay, do see to it that you write your name over here like this: V in underscore your name, V out underscore your name, and you take the full print screen of it, right? And of the input and output also for each case. So you open up a Word document and take on, continue to take your full print screens of every part of it. Right? So for frequency response, you can take it for any one value, right? And for the for the measurement of FL and FH, you can take it for that. Fine. Now let me show it to you how to measure the bandwidth. So let's come back over here again. Sorry for this. Okay, fine. So what will be my bandwidth now? As I've determined earlier, the bandwidth will be FH minus FL. Now how much is FH? It's 77. I am 0.02 into 10 raised to 6 minus 483.958. Now can you tell me how much will be this? This will be approximately equal to 77 megahertz only. Why I'm saying this? Why I'm saying this compared to 77 into 10 is to 6, 483 value is very, small number, right? That is why my bandwidth will be equal to the higher cutoff frequency only, mostly, in most of the cases. And I'm not sure how much you are getting, but if you're getting a higher cutoff frequency in the range of megahertz, then the bandwidth also will be in the same range. So the bandwidth of this amplifier is 77 megahertz. Okay, and that's how you calculate the FL, FH, and bandwidth. Now, is the higher cutoff frequency, lower cutoff frequency, and bandwidth measurement clear to you, everyone? How to do that in the LTspice? Clear to you? Please
Yes, sir.
confirm. Okay, very good, very good. So this you have done it. Everything you have done it with part 1 as bypass with bypass capacitor CE. Now there is part 2 also. So I am just combining this part 1 and 2. You all have to do it separately. Okay, remember that. Okay. So for part 2, I am writing over here for part 2. For part 2 CE amplifier with, so everything remains the same. CE amplifier without coupling bypass capacitor CE. Okay, don't confuse by this CE and this CE. This CE is common emitter. Okay, this CE over here is common emitter amplifier, BJT amplifier, and this CE is the bypass capacitor. Okay, so here when I write over here CE amplifier without bypass capacitor. So for CE amplifier without bypass capacitor, what you have to do? Repeat the entire procedure again. What you have to do? Whatever I have been discussing with you all for last 20 minutes, repeat the entire procedure again as it is. But when you go over here, close this, close this, maximize the screen. So what with this procedure, just take a scissor and cut the wire. The CE will be disconnected, and repeat the entire procedure as I've explained for the frequency response. Okay, so everything you have to do again. Again, you have to set the value of all the frequencies, right? All the frequencies you have to take. Again, that entire table will be different. The gain values and the Vout value will be different. Again, you have to set it at 40 millivolt. And again, you have to measure the FL, FH and bandwidth in the similar manner. Is that clear? Without bypass capacitor, what has to be done? Just disconnect this wire. That's it. And repeat the entire procedure for frequency response and FL, FH and bandwidth measurement. Is this point clear to you, everyone? Absolutely clear? Hello? You all have any doubts in this? Can someone confirm? Part 2, how you have to do the frequency response without
Yes,
and
sir.
with bypass capacitor. Okay, very good, excellent. So we have completed 2 parts of the experiment. Okay, in this experiment of frequency response, with the aim of study the frequency response of BJT amplifier, we have completed the part A, which is frequency response, and part B, part 1, which is common emitter amplifier with bypass capacitor CE, and part 2 is common emitter amplifier without bypass capacitor CE. So you have to just disconnect the bypass capacitor CE. We have completed the frequency response, how to measure it, take the readings for various frequencies, and then finally how to measure the lower cutoff frequency, higher cutoff frequency and bandwidth. Okay, now let's continue further. The third part, the third phase in this will be transient response. So next we will be discussing about the transient response. Transient response. What do you mean by transient response? Transient response means we have to plot V in versus time and V out versus time, and then test the gain, how much it is. Okay, so let me just mark it. Sorry for this. Okay, transient response, we will start now. One more thing I want to state further before starting with the transient response is your input which will apply. Our input is Vs, right? So input applied will be 40 millivolts peak to peak. Okay, input applied will be 40 millivolts peak to peak. Right now, this is very important concept coming up next. What frequency you will decide, or what frequency you should work the amplifier at. Now, can anyone tell me what was the frequency given to you in the write-up? What was the frequency given to you all in the write-up for the transient response? It's not written, it's not mentioned. So you let me know if it is not mentioned. Please quickly let me know.
So it is not written.
So you have to decide what should be the frequency. So how will you decide? I will let you know. So remember, this is my amplifier frequency response. What do I want from my amplifier? To provide a constant gain, na? And where is the reason I'm getting a constant gain? Where is the reason I'm getting the constant gain? Roughly around 10 kilohertz to around 100 megahertz. I'm getting constant gain. Correct, na?
Yes,
If
sir.
I go at 1 kilohertz, my gain is falling down. If I
Yeah.
go at 100 megahertz, my gain is falling down. So what frequency you will take? Can anyone tell me where my gain is constant? And where is my gain constant? From 10 kilohertz to 10 megahertz. So I can take any frequency in between that. Do you understand? So from here, I can take the frequency. I can easily see that at 10 kilohertz, the gain is constant throughout. So what I will do is I will take the frequency as 10 kilohertz. Okay. So that's how you decide the, you know, just wait a minute. Okay. So that's how I will decide the frequency as 10 kilohertz. Everyone understood why I took as 10 kilohertz? Hello? Everyone has followed? Any doubt in understanding? Why
No,
I
sir,
want
follow.
10 kilo? Yeah, why I want 10 kilohertz is because at 10 kilohertz my gain is constant. So I'll write it down over here that select 10 kilohertz since at 10 kilohertz gain of the amplifier. That's why we have done the transient response first. Gain of the amplifier is constant. Okay, fine. Now can anyone describe me the table? What was the table looking like for transient response? I guess you had input over here, right?
Yes, sir.
What was the, can you read out what was written over there in the table? Input
Yeah,
amplitude.
input signal.
What is the next part? Output.
Yeah, V out. And then gain in decibels.
Okay, perfect. So what we have to do is input signal. Now what does the input signal meaning? We will take two readings now. We will take it as 40 millivolts peak to peak. I will show you one sample case only. And along with 40 millivolts peak to peak, you have to define the frequency 10 kilohertz. I'll write it as at 40 millivolts and 10
Sir, one
kilohertz.
doubt.
Yes, please ask.
Yeah, sir. So you asked this table for transient response or frequency response.
Transient response.
Okay, the table which we have not yet filled, right?
No,
Yeah. So
this is
so
transient response.
yeah. So the columns are input signal, V out theoretical, and V out practical.
Okay, perfect.
Yeah.
So I will add one more. So V out theoretical, right? And then we
Yeah.
have V out. That is what we will be doing today, calculations. So V out of t, na? Why I'm writing t? Because it's a function of time. And then gain in dB, theoretical and practical. We can do that. We can later on find out the gain also. No problem with that. So let me add that column. No harm in calculating something extra, right? Because that is
Yes,
a
sir.
part of your theory also. So
Yeah.
gain in dB. Now I will bifurcate over here. This will be theoretical, right?
Right, sir.
And this will be simulated, practical. Simulated or practical. Again, this will be theoretical gain. Why I'm additionally adding the column of theoretical gain? Because in your in your theory lectures you will be solving this by default only. So it's better to calculate this. How will you measure? How will you check whether the simulated voltage is and the theoretical voltage is coming? So for theoretical output voltage, you will require gain. So we have to do this, and second reading will be like at 20 millivolts, peak to peak. P to P means peak to peak value. Okay, P to P means peak to peak value. This I have to select. Okay, sorry for this. 10 kilohertz. Okay, is this clear? This is what we will do. And now we will immediately fill the values for, and this you have to do it for what? With bypass capacitor and without bypass capacitor. Will be two more readings over here. Two more columns will be there with without bypass and unbypass. So we will do that, no problem at all. Okay. So first of all, this is clear. The table is clear. V out theoretical, V out simulated, gain in dB theoretical, and gain in dB simulated. So let's start. Let's start. 40 millivolts peak to peak, 10 kilohertz, right? So I'll go over here in the. I'll close the frequency response plot. Now I don't have to select AC response, right? I have to select one frequency. So what you do is right click over here, delete this one, keep it blank, uncheck this, and then go to sine wave. Go to sine over here. In the sine, give DC offset as 0. Now this amplitude is this amplitude is the peak amplitude, right? So peak amplitude will be 20 millivolts, but peak to peak has to be 40 millivolts. So 40 millivolts peak to peak has to be written as 20 millivolt over here. Understood this? See, whenever we write over here amplitude, it is a peak amplitude, but we want peak to peak 40 millivolts, right? So that's why we write over here 20 millivolts peak. And what is the frequency? 10 kilohertz. 10 kilohertz is the frequency, and I'll click on OK. So when I do that, I'm shooting my circuit to transient response. Now I have applied at one frequency. See, remember earlier I was applying various frequency range, but now I want my circuit to operate at one frequency only, at 10 kilohertz, which I know its gain will be stable over here and constant. So I've applied 20 millivolts peak value, and frequency is 20 kilohertz. Everyone completed up till here? Please let me know. Anyone lagging behind? Or I should repeat any step?
Completed.
Okay, very good. Now we have to plot V in versus time and V out versus time. Okay, we have to plot V in versus time and V out versus time. So let me put back this capacitor, CE capacitor. I have connected back my coupling, bypass capacitor CE, and now I'm about to simulate the transient response. So for transient response, I will go over here, click on simulate, click on run. Your transient is written. There is no hard and fast rule over here. Okay. Now, what will be my stop time? Now, what is my frequency? 10 kilohertz. Can anyone do it in the calculator? What is 1 divided by 10 kilohertz? 1 divided by 10 kilohertz. It will be 0.1 millisecond. Just check. Please confirm. 1 divided by 10 kilohertz is how much? 1 divided by 10 raised to 3.
Yes.
0.1 milliseconds, right? So ideally I should write here 0.1 millisecond. But if I write here 0.1 millisecond, I will get only one cycle. So let's write 0.2 milliseconds. So I'll get 2 sinusoidal cycles. Okay. And then press on OK. Then press on OK. Then you will get a blank screen with the time axis from 0 to 200 microsecond. Okay. That means 0 to 0.2 millisecond. So here I'll right click. I will right click, click on the add trace. And before doing that, what I will do, sorry for that. Before doing that, I will right click, click on the add plane plot. Click on the add plane plot. So now you have 2 subplots over here. So for the first plot, I will add over here V in. For the first plot, I will add over here V in, right? So now you can see peak to peak value is how much? This is a sinusoidal signal with 2 cycles, and the peak value is 20 millivolts. My negative peak is minus 20. So peak to peak value is 40 millivolts. Is this clear? So that's why we write over here 40 millivolts peak to peak 10 kilohertz. You can check with it is 10 kilohertz also. And I'll come to the lower plot, and I'll plot over here at trace V out. So V out is coming like this. Okay. So are you all getting the plot up till now? Everyone. Are you all getting this plot? Okay. Now do some
one doubt.
Yes, yes.
So we also got the same graph. Even if your resistor values are different, we got the same graph.
Yeah, we will discuss about that. Maybe coincidentally we will see. We'll come back to it at the end. So let me complete the end.
Input graph is same. Output graph is different.
Input graph. See, input graph will be same for any circuit, right? Output will be different because the gain is different.
Yeah, sir.
Okay. Now do one thing. Everyone do one thing again. Now you have understood the concept, right? Why we have given a point. Again, let's go to edit simulation command. Why we have given 0.3 milliseconds, right? Now make this 0.4. So I should see 4 cycles, right? Or 0.5 or 0.4. So I should see 4 cycles now.
Yeah.
So let me simulate it again. See, I can see 4 cycles now. Okay, clear it is?
Yes.
Everyone clear about this? So this is my input output graph. If I want to see 4 cycles, I can plot it 4 cycles. Now, how to measure the output? What I have to do is I have to measure the, again, I go back over here. I have to measure the V out value, right? Peak to peak value. How much is that? So that I can easily measure by keeping the cursor over here, maximum value. I can note down this value 1.29 and I'll add it to this value -2. So 1.29 minus of -2. So that is the value which I'm getting. Again, I repeat, I'll go to the peak value over here. I only want the output now. Input, I know how it will be, right? Now remember one more thing. You have to take the print screen of your, at your place of your print of your values once you get this graph and of the circuit itself, because it is changed now. Okay. Then remember one more thing over here. Remember very crucial thing over here. One more thing. If you see carefully over here, input will be remaining the same, right? Throughout. Output is out of phase with the input. Now I hope that you understand what is out of phase and in phase. 180-degree out of phase. Output is 180-degree out of phase with the input. So what does that mean? Anyone can tell? What does that mean? I can add one comment over there that my V out of T and okay, not and V out of T is 180-degree out of phase with V in of T. With respect to, basically, we can write V out of T is 180-degree out of phase with respect to V in of T. What does this mean? Anyone can tell me? What does this mean? Come on, answer this
R is
question.
equal to pi.
No, not pi, not pi. It means that output is negative with respect to input. See, I'll explain it simply. When my input is increasing, my output is decreasing, correct? And when my input is reducing, my output is increasing. So they're out of phase. What do you mean by out of phase? Means my output sign is negative. My output is negative with respect to input. That is what the meaning is. This will say that my output has a negative sign. Whenever I plot, whenever I write something over here, whenever I write any reading over here, it will be negative. Are you getting the point? What's the meaning of V out of T out of phase with the input? Okay, I'll write over there. My output V out of T will be negative. Will have a negative sign. Okay, I will write over here. Output will have a negative sign. So what will happen when, let's consider another situation. Let's say that hypothetically output is, input and output are in phase with each other. In phase means if input is increasing, output is also increasing. And if input is falling, output is also following. So whenever input and output are in phase, the output voltage will have a positive sign. Is this point clear to you, everyone? Please understand and let me know. Clear it is? Yes or no? These are concepts.
Yes.
So, okay. Now let's measure the V out value, simulated value. Okay. So how to do that? Now peak to peak value is slightly difficult. So what you do is you use the dot measure statement. You use the dot measure statement. Let me use the dot measure statement now. Let me delete this. So I will use a dot measure statement. I'll write dot measure. Dot measure. You don't write it, just wait. Dot measure. I'll write V in. V in is the reserve word. I mean, not a reserve word, user defined word. Peak to peak value. Then I'll write V of V in underscore my name. That's the label I have given. Okay. So this what this statement will do? This statement will directly give you the value of V in peak to peak in the word, and it will store it in the in the user defined variable V in. Then I'll write dot measure V out. Peak to peak, PP stands for peak to peak, V out underscore my name. Okay, so this will measure the output peak to peak value. Then I want to calculate the gain also, so I'll write dot measure gain. Gain will be, and I'll write param. Just write this. I'll explain later. Gain param V out underscore V in. Okay, so once you have written this, statements, and I think you have to write similarly. Whatever label you have given, don't write my name over here. You write your name, which label you have given. V in underscore your name, V out underscore your name. And then copy this. Then come back to the LTspice, right click, go to draft, go to spice directive and paste this. Paste this and click on OK and attach it in the screen. Understood what we have to do? Again, I repeat, write the statements, V in underscore your name, V out underscore your name, copy this over here, go back to LTspice, right click, go to draft, go to spice directive and add those statements over here, click OK. So these statements are added. Okay, now I will let you know what the statements will do. Again, I simulate, I'll get the same plots, V in versus time, V out versus time. Okay, and now what I will do is I'll go to view, go to spice error log. When you go to spice error log, here if I expand it, okay, here I'm directly getting the values, V out value, gain value, and my V in value is also there from 0 to 4 microseconds. I guess how much it is time in the time. This is the time actually 0 to 400 microseconds. Okay. So here it is showing again. I repeat, go to view, spice error log, and these values. So everyone getting these values for your circuit, please confirm. Everyone getting these values for your circuit. Anyone facing problem? Let me know immediately. Come on, people, I have to proceed ahead now. Hello?
So after writing those commands, can you repeat the step?
After writing those commands, have you pasted on the LTspice?
Yeah, sir, I have.
Now you run the simulation.
Okay.
As it is, it will run. So open the schematic in detail. Go to view. Click on the spice error log. There you will have all the values. You can maximize this window. Did you got it?
Yeah, sir, I got. V in I got as
No,
0.039.
Don't set the output value. You can keep it with yourself. Don't set the
Sure.
output. But are you getting a finite value of V out and gain?
Yeah, sir. All the
Okay.
three values I am getting.
Now only limitation of this will be this dot measure command is that this is very accurate. It will give the magnitude of V out. But while writing, we have to write it minus. Why we have to write minus? Because we have seen that in the input output plot, it is out of phase, right? So let me add these values over here now. Everyone has understood how to measure the transient response. This is how we do it. How to do the transient response? Okay, it is everyone. Everyone followed. Anyone still have a doubt? Please, you can ask right now because I will be proceeding ahead. Clear it is. So V out simulated value, how much I got? I'll go to view. I'll go to spice error log. So here it is written 3.8 48. So here it is how much? Minus 3.48. You understood now why we write minus? And what is the gain in the simulated value? Gain in, actually this is not in dB. You might have to convert this in dB. This is just the gain. Okay. So let me just add, oh sorry for this. Let me add one more column over here, just the gain, simple plain gain. So gain in simulated without in dB, not in dB. Okay, how much is that? Minus, again it will be minus 87.199. Now anyone can tell me how to convert this gain into dB? How will you convert this into dB? Anyone? 20 log to the base 10 magnitude of AV. Okay, you take the magnitude of AV and that will give you the voltage gain in dB. So this will be gain in dB. Or you can, what you can do is, I will make it simplified for you all. So what I will do is I will make a simplification over here. You just calculate the gain V out upon V in. That's it. No need to calculate it separately. So what you do is, I showed you the formula how to convert into dB, but you can just do it like this also. If you want, you can do it in dB also, but for checking work, you can check it out. I will show it to you how to check it, the readings. Okay, so if you want to convert gate in dB, you have to put 20 log to the base 10 mod of AV. So in my case, 20 log to the base 10, 87.199 value is around 38 dB. So this is, I'll just write for my understanding over here. This is 38.81 dB. Normally in your numericals, gain has to be calculated in dB. Is this clear to you, everyone? How to do it? How to measure the gain, voltage gain, and the V out value? It will be negative, and I showed you why it will be negative. Vs and V in and V out are out of phase. Is this point clear to you, everyone? Everyone has understood how to measure the simulated values? Quickly tell me, please.
Yes, sir.
Okay. Now this was for this, whatever was for what? Bypass value. Let me do it for unbypass. This is was with capacitor. Okay. So let me do it again and copy it down. So this will be for unbypass part. Let me give me 1 minute, please. Okay. So I'll take over here and paste it again, and this will be for unbypass part. Let me add it over here. Okay. This one will be without bypass capacitor. Okay, this table, and this table will be this table which we have done it before. What is that? This will be with bypass capacitor with CE. So right now we have done it with CE, right? So this is without bypass capacitor. The readings will be different, right? So let me rub it out over here. I hope the screen is visible to you all the time.
Yes, sir. Visible.
Okay. Now what I will do is I'll go back over here. Nothing I have to do. Only one change I have to do. Just disconnect the capacitor. Disconnect the capacitor. Now again I'll simulate. I'll got the plots. You will say what's the difference? There's a lot of difference which is coming up. Here I am getting a gain. If I remove the capacitor, then I am getting a different gain, right? And what's my gain over here? My gain is less than 1 if I remove the capacitor itself. For my reading, I am getting a gain of less than 1 itself, right? So I note down that reading over here. For my case, I am getting this much. For if I remove the capacitor, what reading I am getting, I'll note it down now. So I am getting over here the reading of at around 40 millivolts peak to peak value. How much I am getting? The V out value is 0.028 volt. Okay, simulated value. And what's the gain in simulation? Gain in simulation is 0.701. Okay, so those are the values which I'm getting. So what you do is, without bypass capacitor, instead of taking 20, you take it as 80 millivolt. Okay, or you can take it as 100 millivolt also. So just do this, take it as 100. For unbypassed part, with coupling capacitor, with bypass capacitor, you can take it as it is. Without bypass capacitor, you are getting these readings. Okay, and if I want to convert this in dB, I'll take 20 log. I will do at my calculator over here. I'm just showing you. It will be like you have to take the magnitude 20 log to the base 10 of 0.701. So I am getting a gain of around. So I'm not sure about how much y'all are getting, but I am getting the gain over here of about. Just 1 second. Just 1 second. Is the screen visible to you? Hello?
Yes, sir. Microsoft whiteboard screen.
Yeah. So please carry on your work and note down your values. My screen is stuck a little. So as soon as it operates, as soon as it is responsive, I will continue. Please carry on with your observation table. Complete your transient part. And as soon as my screen is again functional, I will be showing you all the this thing, next part, the calculation part, how to measure calculated values. Okay, so please cover it up.
Okay, sir, a doubt. I
Yeah.
have.
Yes, yes.
So in bypass, we took for 40 millivolt peak to peak, we took 20 millivolt as our
Yes, 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 correct.
right. Yeah. So for 20 millivolt, we'll take 10, right?
Yes, 10 millivolts, exactly.
Yes.
Okay, is this point clear? Let me see if my task manager will help me out. You all just simulate again and let me just continue. Huh. Now it is again functional. Let me run the Microsoft board again. So you all please carry on with your work. I will give you all. I hope that transient response is clear to you. Everyone, it is clear. Please, I want to receive the response from 1 or 2 people. Yeah. Up till now, whatever we have covered, y'all have understood? Yes or no? So please, 2 or 3 people. I don't want the same person to repeat. Please, 1 or 2 of y'all, please let me know whether you have understood this.
Yes, sir.
Yes, sir. Yes, sir.
Okay, good, great. Okay, I was about to complete that value that I was getting 20 log to the base 10, 0.701. So I got the value of minus 3.08 dB without CE. In your case, it might be different, huh? So don't go by this readings. Okay. How much you all have? Where have you reached? Have you started with transient response? Anyone?
Yes, sir. I did it for bypassed 40 volts peak to peak. I got some
Millivolts,
values.
millivolts,
Yeah,
millivolts.
sir. Yeah.
40
For
millivolts peak to peak.
40 millivolts peak to peak. Yeah, and 10 hertz. So I tried for unbypassed. So there I'm getting an error.
What error
This
you are getting?
circuit has floating nodes, and so I'm not getting any values over there.
नहीं
So
नहीं remove the capacitor also.
completely I'll remove it.
I agree. I agree. What is happening is I'll explain it. Wait.
Yeah, that
You might
capacitor
have.
is
Okay. Okay.
recognizing as
Wait.
floating.
Have you given any name over here? Base, emitter, collector.
No, sir.
Okay. So you have removed this, na capacitor. So completely remove the capacitor. So
Yeah, I
additionally,
removed it now.
please do one more thing. Additionally, please one more thing you have to add. This will help you out in your calculation part. Just right click on the this thing label and click give base B. B stands for base. This is your collector and this is your emitter. So this I will name it as C, capital C, and this label will be capital E. Just give it and keep it ready. B, C, and E. Base, collector, emitter.
So
Okay.
for previous screenshots, we don't have this. Is it okay?
No problem. From now on, follow this.
Yeah.
No, not necessary. I require
Okay, sir.
this for calculation. I require that for calculation. Let me add it, put back my capacitor, and let me see how much value you're getting. You all are sure that in your write-up, RSig is not present. There is nothing connected over here. Directly, the input is applied to the capacitor CC1. Please confirm. Please
Yes,
confirm
sir.
that. Directly, na? No, nothing connected over here.
Yes.
Okay, fine. Yeah, fine. No problem at all. So please continue. I have showed you the entire technique how to do the experiment. Now, in 2 minutes time, I will be starting out with the calculations. So please be attentive in that. So I'll give you 2 minutes more. You can complete the later part on the, afterwards. So let me prepare something till then, and then I will carry on my work. Okay, so you carry on with your own work. I will be showing you all something else now.
So now I got the values for unbypassed as well.
Okay, very good. So you keep the table ready. Now we will focus on the calculation part. Calculation part is only for the transient response. Am I correct? In your write-up?
Yes, sir.
No. In your write-up, only transient response have this thing. What can I say? To be theoretical calculations. Rest frequency response doesn't have it. Correct?
So it's not mentioned specifically. In the calculations tab, it is mentioned as AC analysis.
No. Theoretical values where it is written
Yes, sir. In the
in the
table,
transient.
only transient response has that column.
So
Theoretical.
for next 20 minutes, I am going to show you how to calculate it. You want me to show it to you, explain it in simple language,
Yes, sir.
or you can do it on your own. I'm giving you the option. I can stop the recording right now, and you can complete the calculations on your own, or you want me to show it patiently. What do you want
Sir,
me to do?
due to show us.
Acha. So please be attentive now. Very, very attentive. Let me just delete this stuff. Okay. Let me write few lines over here. This is GM into RC. Okay. So is my screen visible?
Yeah.
Okay. So here the heading of this is common emitter amplifier with CE. Okay. With CE. So if I have a CE, this won't be there. This will be bypassed to the ground. Okay. Fine. So here there will be CE, and the formula is this. This is coupling CE amplifier without CE. Just let me complete it. Then I will be sharing with you all how to do the calculations. CE okay. CE amplifier. Calculations for both are different. CE amplifier without CE. I hope you have understood now what is CE. This is bypass capacitor. Okay, fine with it. Now let me start with the calculations. Everyone pay attention now, please stop your work. You can carry on later on. So, how to calculate this is actually a common emitter configuration with a voltage divider biasing. So everyone knows how to calculate a voltage divider biasing, right? So you all will be calculating VTH, RTH, IBQ, ICQ, RPi, GM, and RO. Okay, I am not explaining in detail how to do that. The formulas are given over here. I'll just repeat it. So for VTH, for my case, it will be R2. I mean, the formula remains the same. R2 divided by R1 plus R2 into VCC. So I am getting 4. You all will get different values. RTH is R1 parallel to R2. I am getting 8 kilo ohms. You all will get different. IBQ will be VTH minus VBE divided by RTH plus 1 plus beta times RE. Okay, so I am getting beta as 325 and RE value is 2K for my case, and VB I've assumed it to be 0.7. So I am getting IBQ as 5 microamperes. ICQ will be beta times IBQ, that will be 325 into 5 what I got, 1.625 milliamperes. Okay, so I'm not giving much emphasis on this. This is the calculation which is being covered in your numericals, right? Let's come to small signal parameters. So small signal parameters, we have uh, RPi, GM, and RO. What is RPi? RPi is there in the small signal model, GM is the transconductance, and RO is the output resistance of the BJT. RPi is the input resistance of the BJT. RPi formula is beta VT upon ICQ, so I got it as 5.2 kilo ohms. GM is ICQ upon VT, I got it as 62.5. VT is the thermal voltage, its value is 26 millivolt, and RO value is the output resistance. Now VA is the early voltage. Let me add it over here. VA is the early voltage. So probably this value might not be available to us. That's why we are not calculating theoretically over here. We will go for that simulated value. VA is called the early voltage. You might have studied it when you studied the BJT. Okay, its value is RO, VA divided by ICQ. So I'm getting these readings. So calculated values. Now I will show you how I got the simulated values. Okay. So let me go back to this column of this not required for you all actually in detail, but you will require the calculated values of this and compare it with the simulated value. So yes, you might require it indirectly, but not directly you have to write it. Okay. So what I will do is I'll again go back to my amplifier. This is my amplifier, right? Everyone is listening? I'll delete this part. This is not required now. Transient response also I am required now. Everyone in the same page? Can someone respond?
Yeah, sir.
Okay. Now what you have to do is, this is the DC analysis, right? So you have to go to simulate, click on run, and then you have to select DC operating point. In the edit simulation command, select DC operating point, then click on OK. Once you click on OK, you will get a screen. Okay. You'll get the screen operating point. Just close that screen. Okay. Again, go to view and go to spice error log. Again, go to view, go to spice error log. When you go to spice error log, you can maximize this part. Can you see this part now in my screen? Visible, right? So what is IB value? IB value for BC 547 B. How much is this value for my circuit? 5.08 microampere. See, it is over here. IC value is 1.65 milliamperes. GM value is also over here, 6.28. I mean, it is 6.28 into 10 raised to e raised to minus 0.2. 0.2 is 10 raised to minus 2. Okay, so it is 62.8 milliampere per volt. RPi value, can you see this RPi value? 5.12 into 10 raised to 3. E plus 0.3 is 10 raised to 3. So 5.12 kilo ohms, and RO value 4.29 into 10 raised to 4. That will be 42.9 kilo ohms. So did you got how we have got the simulated values? Everyone understood? Please confirm.
Yes, sir.
Okay. Now there is a concept of beta. There is this factor beta of the transistor. So there are actually two betas, beta AC and beta DC. Okay. So beta AC is associated with the DC calculations and beta AC is associated with the AC calculations. Okay. Whenever we measure the gain and all. So over here, beta AC DC value, how much is this? Can anyone tell me from over here? Can we tell me the number? What is beta DC value? From the in front of your screen, what do you see?
3.25 into 10 raised to 2.
So how much this should be? How much this value should be? 325, right?
Yeah, sir, 325.
And beta AC value is 322. So they are more or less same. So you can take the similar values over here. So now you will always have a question now. While solving this numerical, what's the beta value? So how did you got the beta value of the transistor? It's not defined, right? So how to check the beta value of the transistor? See here I have written over here the BJT parameter beta. But how will I know what's the beta for BC547B? In this manner. In this manner, I will get to know the beta DC value of my transistor BC547B. Is this clear to you? How much you are getting the beta? Can someone tell if you have done the analysis? Someone has simulated this manner. So how much is the beta value for y'all?
So I need 2 minutes and then I'll confirm.
Some of you can tell. Let me know quickly, please. Please confirm quickly. Anyone with the beta value, how much you all are getting for your circuit? Operating point, just go to Spice error log and maximize this part. You will get beta DC value directly. So is someone getting it? Please tell fast because we have 10 minutes only. I'm waiting. Yes.
Yeah.
How much did you get? Read it out. Please read out the value.
Sir, the heading is not actually beta AC or DC.
Then sorry. Did you did this procedure? Are
Yeah,
you
sir.
getting
In
in the
DC.
view?
Yeah.
In the view, you go to Spice error log.
Now I got it, sir.
How much is that value? Tell me the value. That's it.
Beta DC value I got as 310.
Okay, very good. Very good.
Beta AC value I got it as 305.
Okay, okay. Very good. So 310 now for you.
Yes, sir.
Okay, okay, okay. Fine, fine. Good. So beta value is required for your calculation. Now I'll be showing you the calculations only. So listen very, very carefully. See, I am not teaching you again how we got this small signal model. Okay. So this model over here which I've drawn, its heading is mid frequency small signal equivalent circuit. And I've replaced my BJT with the hybrid pi model. I'm not doing the derivation again. Now only addition I have is RL value. Okay, only addition I have is RL value. Then I'll proceed ahead from here on. I'll take on from here. So if I have a I mean additionally I have RL, right? Rest all is same. So what I will do is I will cut this part over here and I'll add a RL value, load value, right? I'll added the load register RL. Okay. Now if I've added the load, how will it change the formula? Before the load it was GM into RC. Now what it become? RC will be parallel to RL, right? So formula will be this. This will be the formula. Okay. V out upon Vs, the voltage gain, I can write it as AV will be equal to minus GM into, okay, sorry for this, GM into RC parallel to RL. Is this clear to you, everyone? So this you have to calculate. So let me just do it quickly for my case. And I have to confirm with the values over there. So in my case, the GM value is how much? The GM value is calculated value is how much? Let me just add it over here. GM value is in my case 62.5 milliamperes per volt, right? So I'll add that value over there. In my case, the GM value is 62.5 minus 3. And what is RCA parallel to RL in my case? RC is 4K and RL is 2.2K. Okay. So you all have to do the calculation according to your values. So in my case, the value of RC is 4 kilo ohm. So 4K parallel to 2.2K. Okay. So I will calculate this now very quickly. So 4K parallel to 2.2K. I will do that in my calculator. So you can do for your values. 4 kilo ohms into 2.2 kilo ohms divided by 4 kilo ohms plus 2.2 kilo ohms, and that value is, I'm getting it as, I got this value as 1.41. I'm getting for my readings, huh? Y'all have to do it for y'all. 1.419 kilo ohms. Okay, and multiplied by, I have to multiply it by 62.5 e raised to minus 3. Okay, so 62.5 e raised to minus 3 into 10 raised to minus 3 into 1.419 e. So here the gain is coming out to be, I am getting the gain as minus 88.68. So that's the gain I am getting, 88.68. Now is this gain proper? Let's check it out. How much I got? 87.199, na? Correct. And my gain now, right now, is how much? 87.199. Okay. So what could be, is it close enough? Yes. My gain is minus 88.68 theoretically, and the simulated value is minus 87. So you see over here, you saw over here, it's quite close. But there is something missing over here. Can anyone tell me what is missing? Anyone? Something is missing. Can anyone tell me? Yeah. So listen, we have in a model, na, RO is also present, na? RO, small RO. You saw in this readings, RO was there, and the simulated value was 42.9 kilo ohms. So that we have to add over here. That we have to attach over here. So that if we add, if I add that value over here, what I will get, I'll extend this further. So that is a part of the circuit, right? So let me add it over here now. Just give me a moment. Add RO value, which is a part of this hybrid pi model. For practical cases, it will be there. So this is my RO value. Now, anyone can tell me what will be the formula become? Come on. Please let me know what will be the formula now. Will it be RC parallel to RL parallel to RO? One more thing will come. RO will also come. And what was the RO value? Did you get the point over here? Okay. One more thing will come, that is RO. So right now this will be in parallel to RO. What's the value of RO? We will check it out. What's the value I got over here? 42.9 kilo ohms. So you all also might note it down the theoretical value, and this is 42.9 K. Okay, so I have to do 1.419 kilo ohms into 42.9 kilo ohms parallel. So I will get some value. I'm doing it in my calculator. 42.9 K parallel to 1.419 K. Okay, let me do it. 42.9 kilo ohms into 1.419 kilo ohms divided by 42.9 kilo ohms plus 1.419 kilo ohms. So I'm getting the value as, this total value I'm getting as, okay. So this value I got it as 1.373 kilo ohms. So now if I multiply 62.5 milliamperes, I mean milliampere per volt with 1.31, 371 kilo ohms, how much I will get? I'll multiply 1.3 kilo multiplied by 62.5 milli. I am getting it as how much? Close to 85.81. So this is my exact value. 85.81. That's the value I am getting over here, theoretical gain. So I can write over here, theoretical gain is minus 85.81. Did you all understand how to get it? Everyone? Hello, can someone confirm? Calculation you all have understood? This is how you have to do your calculations. For, can someone reply and confirm?
Yes.
Okay. Now quickly, we have almost reached the time. I'll just show you the formula how to do it without bypass capacitor. I mean without bypass capacitor. Here, even if you ignore RO, the readings is not much different. Okay. Even if I ignore the value of R naught. Now some of you might not have this value of R naught, right? So even if I ignore this value RO by this, earlier what we were getting by ignoring the value, minus 88 point something, right? 88.68 something. We got it. If we don't consider RO, so this is without RO. So y'all are free to take without RO also. It won't make much difference at all. But even if you consider, it's absolutely fine. Okay. Now let me ignore the value of RO over here. Let me ignore the value of RO and only add RL over here. So what I will do is I'll add RL over here. Okay, this has to be added over here. Let me add the ground here and add the RL value. RL values over here, right? Fine. So now what is the formula? So this is common emitter amplifier without bypass capacitor. So I'm not going into details. Directly I'm telling you this is the formula. If RL was absent, if RL was not there, then this was the formula. AV was equal to, or output upon input was equal to, minus RC divided by 1 upon GM plus RE. Now this you have already studied in your lower semester, so I am not doing the derivation or showing you all how we got this, but this is what we have, right? Now if RL comes into picture, what will be the change? How will the formula change? Ignore RO. So how will the formula change? Anyone? Here I will get parallel to RL. Here I will get parallel to RL. Okay, only that will be the change. Fine over here. So let me do that calculation over here quickly and then I'll leave you. Is minus RL parallel to RC parallel to RL. So RC parallel to RL already we have done over here. So that is actually 1.419K divided by 1 divided by GM, which is 62.5 into 10 raised to minus 3. Correct? Plus RE. Now RE value in my case is how much? 2 kilo ohms. Okay. So in my case, the value of RE is 2 kilo ohms. Okay. I have to do this calculation now. So let me use my calculator. Just 2 more minutes and then we'll wind up. So I have to do 1 divided by 62.5 milli. 1 divided by 62.5 milli is coming out to be 16 in my calculator. So I'll further write it as 1.419 divided by 16, just the number 16 plus 2K. Okay, and this value of AV will be, let me delete this part over here. For this value, I am getting it as minus, let me do the calculation now, 1.419K divided by 16 plus 2K. So I am getting the value as minus 0.703. I am getting the value as, by calculation, 0.703. So this is my answer of the voltage gain. Okay, minus 0.703. So I'll write it down over here. Okay, theoretical, how much I got? I got it as minus 0.7, okay, 0.703. Is this clear? Is it completely matching? See over here. Everyone following this? How to do the calculations now? Please reply. I have showed you the calculations for the gain also. Clear
Yes,
it
sir.
is?
Yeah, sir.
Now, ho- how to get the V out value? Now, V out value is very simple now. Okay, let me show it to you one last thing and then we will wind up. Okay, so let's say that I got it as 88.68, right? Let me confirm that it is whether it is 62.5 E3 into 1.419K, 88.68, correct, without arrow. So I got it as 88.68. So how to calculate the V out value from here? V out value from here, how to do the calculation? Let me show it to you. So over here, see, let me just, yeah, voltage gain is basically, let me use red color basically. Voltage gain is what? V out upon Vs, correct? And let's take a sample case that, okay, what happened over here? Yeah, let's take it now. We have the value of the voltage gain, we have the value of Vs, we will just have to calculate V out. So how we can calculate V out? V out will be voltage gain into Vs value. So in our case, we were getting the voltage gain as how much? Minus 88 point, okay, let me use a black color over here, minus 88.68 into what was the Vs value? What was the Vs value? 40 millivolt, right? So 40 into 10 raised to minus 3. So your V out value will be, your V out value will be in my case minus 88.68 into 40 millivolt. And I got it as, how much is that? Minus 3.547 volt. So this is how you will get the observed value of the V out value, minus 3.547. So here in the table, I'll write it down now, my V out theoretical value. Understood? You will require the value of gain. Obviously, you will require the value of gain. So how much was that? Minus 3.547 volts. Okay, clear how to do it? Similarly, for without the bypass capacitor over here, let me quickly calculate. So here I will directly calculate your V out. Okay, sorry, I have to use a black color or a red color, blue color, let's say. So V out will be equal to the voltage gain into Vs, which is input. So that will be basically V out will be equal to voltage gain is minus 0.703 into 40 millivolt, right? Into 40 into 10 is to minus 3. So how much is the V out value? V out value is minus 0.703 into 40 millivolts. So its value is coming out to be minus 0.028 volts. Okay, its value is coming out to be minus 0.028 volts. So let me add it over here, minus 0.028 volts. You're getting perfect, right? Right, as you can see very clearly. Let me change this readings. This I was getting slightly different, right? It was 88. No, that was fine. So here theoretical values, I got it as 88, right? I've not considered RO, so I will write it as 88.68. Okay, now if you see the table carefully, all the values are matching or no? For bypass part, it might slightly deviate, slightly deviation will be there, but for without bypass capacitor, you will get exact values. Okay, now I will show you how these values are coming. Perfectly all right. Everyone clear about this? How to do the transient response and how to do the measurements, calculations? Clear? Someone can acknowledge, please. You have understood this part?
Yeah, sir. So can you confirm our values once we are done?
No. We will later on confirm it. Later on, see what's the meaning of if you are simulated and theoretical are matching, then that's it. If it is too much deviation, then you let me know. Not now.
Right, sir.
Afterwards, after I finish the recording. Yeah.
Okay.
So now I will show you why these readings are correct. Remember when we plotted the frequency response, if I have taken the value at 10 kilohertz, if I had taken the value at 10 kilohertz, I know my gain is almost constant. What was my value of voltage, magnitude of voltage, how much it is? 100 kilohertz, and I said you know around 10 kilohertz to 100 kilohertz, I mean around 10 megahertz actually. Let me write it over here something now. It's very important. Oh, I have to go over here. It's very crucial over here now. Very important information which I'm giving. We have observed earlier from 10 kilohertz till around let's say we go up till 5 megahertz. The gain was constant. Okay, we have seen that now in the frequency response. The gain remained constant, almost constant, right? And how do we made sure of that? We got this kind of a graph, na? We saw that your gain was almost constant, 38.47 dB, almost constant. So at 10 kilohertz, now what happened was, what was the value now? Let me show it to you now. Wait. What was the value? 3.35, right? 3.35 value. So here how much it is we are getting? See, theoretical 3.5. So very much nearby we are getting na at 10 kilohertz also. So that's why, and the gain was 38.81 dB. And what was in frequency response? 38.46. So quite close. So that means whatever values over here we are getting are perfectly matching with the frequency response. Okay. So now if you have any doubts, you can ask. I have explained you everything about the experiment. How to do the frequency response, then the transient response, how to measure the gain, calculated and theoretical.